A buffer overflow lets an attacker execute arbitrary information. A buffer is storing information in a program for later processing, and when we overflow that buffer, we're sending more data than the developers of the program allocated for. For example, we allocate for 100 characters, but the attacker sends 1,000, overflowing this buffer of fixed length we've created. And this is caused by sloppy programming. We should have bounds checking and input verification, and in the case where a buffer overflow occurs, this has not occurred. So a buffer overflow lets us write and execute arbitrary information in memory. This lets the attacker execute the commands of their choosing on your machine. If they're executing the commands of their choosing, they can do anything they want. They can create a backdoor, they can open a TCP connection that reaches back to them, they can potentially get root or system access depending on the context of this application. This was described in Alepht's once Smashing the Stack for Fun and Profit in 1996. You can still view that article on insecure.org, but buffer overflows have remained a common and prevalent attack vector due to long code bases and improper review and validation of code. So still an attack in use today, still a technique in use today, despite it originally being described in 1996. What is the stack? We say smashing the stack for fun and profit. What is the stack? So it's a data structure. It's last in, first out. That's why it's a stack. You put it on, you take it off. And this stores the important information for running processes. So this could be temporary storage of data that whatever your process executable needs. It's what you're using to pass parameters, returning values from functions. What is a function? And we're allocating space for temporary variables. Okay, we'll look at all that in just a minute. What are the key elements? The base pointer tells you where parameters and local variables are stored, so you can reference those later. Push and pop. We push things onto the stack and pop them off. It's last and first out. And the ESP, that's the stack pointer, that holds the address of the last memory location in stack memory. That's where we're stopping. So let's look at an example program. Execution begins in main, and my first line is printf. This will just print hello world onto the screen. And then I call my first function. I'm going to draw what the stack would look like as we go through this function. And we're going to grow from low to high. This is last in, first out. So I call my first function. Those function arguments are going to go on the stack. And then we're also going to add a return pointer. And that's going to provide the address and memory of where main is, so we can actually get back to this main function after we finish executing. And then we're going to go into my first function that was called from the main application, and I create char buffer A and char buffer B. These are for a string. A is 1,000 characters, B is 100, arbitrarily picked. So now that we've defined those will be added to the stack. I'm also going to add a saved frame pointer that will tell me how to get back into my application from these variables. Well, buffer A is added to the stack first because it's called first, and then buffer B is added next because it's called next. And then we ask, what's your best color? Not your favorite color. We're trying to trip them up. We ask the user for input. What are they to respond? We're going to accept. We have absolutely no validation with gets buffer A. So it's going to take whatever they put and just throw that in buffer A. And then it's going to copy that blindly into buffer B. And then we'll return, which brings us back to main. And after we get back to main, I printf success. I debug with printf statements because I'm a bad person. Once this prints to your screen, you know you're a bad person, and also my first function ran successfully. So when we're asking the user for their input here, if they just responded with 1,000 A's, and that was copied into buffer A and then copied into buffer B, well, now I'm just going to have a bunch of A's overriding all the data in my stack because I didn't do proper validation, but it's still getting written to memory. It will overwrite my return pointer. And with that done, now my program's just going to crash. It doesn't actually know how to get out of my first function back into main. Now what if instead of just putting A's, we instead overwrite buffer A and we instead put malicious code in here. Now it accepts the input as a string, but if we put more characters in here than is supported, I can just completely overwrite the saved frame with gobbledygook. And then I can also, as we keep going down the stack, I can overwrite this return pointer with another pointer that's going to put me higher in the stack to run my malicious code. And maybe I just overwrite everything else with A's. I don't know. But the important point is I overwrite this return pointer and have it point higher in the stack so that I can execute my malicious code instead of letting it return to the main function like it's supposed to. Well, what does this malicious code do? The malicious code can do really anything that the attacker wants to, but generally this could be creating a TCP connection to call back to their malware server, or maybe it's just opening a backdoor, a listener, maybe it's executing shell commands, but they're doing whatever they want to get access to your system. And then what is a machine going to do to defend against this? Well, we have something we call address space randomization layout, and that's designed so when I write high address and low address, these are actually addresses in your memory, and to avoid the attacker being able to overwrite the return pointer and point to their own code, we use address space randomization layout, so memory doesn't get stored in the same place every time, making it so the attacker has to guess where their code might be, so we don't have 100% success in pointing to the right place in the stack to execute their code. But we can help ourselves out by adding what we call a NOP sled. No operation. NOP. The attacker is going to add thousands of null operation. It's not going to do anything in assembly. It's just do absolutely nothing. Add thousands of these, so we don't actually really need to point at a specific location in memory. We just generally need to point at memory and have null operations slide into the actual malicious code that we want to execute. NOP. And then you're thinking, man, that sounds like the perfect thing for antivirus to detect. I just need to write a signature, so if I see a bunch of null operations, that's malicious. Okay, that's a great thought. But as you know from your job, there are a whole lot of ways to do nothing. We could add -1 to 1, that's 0, that does absolutely nothing. So we can do nothing in a lot of creative ways to evade antivirus detection. Bottom line, a buffer overflow lets the attacker execute arbitrary code by smashing the stack.